Last time we started section 6.1, we're talking about the set of rational numbers. In particular, the rational number sort of image that we want to have in mind is fractions, where you can write the numerator and the denominator as integers. Those are rational numbers. And we're going to take a look today, start with historical notes. So there's a lot of history behind fractions. Fractions were used a long time ago. The Egyptians used fractions, but they always had numerators of 1. So instead of writing a number like 7 over 12, they would write it as a sum of 1/4 plus 1/3. So that's very different than what we do now, but that's how they used fractions. The Greeks adopted fractions with denominators of 60 from the Babylonians, still presently used in the measurement of angles, right? Our measurement of angles, we like to use 60s. The Hindu developed our modern bar between the numerator and the denominator, and that came into use in about the 1500s. So that bar that you're used to seeing dates back a long time. We talked last time, I had these pictures like this, and I talked about the fact that A, B, and C are all basically the same picture. They're different shapes, but they're a part of a whole diagram. And then the part D was something quite different. And we're going to actually take a look at that next. So these are different kinds of models for fractions. So the first one is called an area model. It says you use a rectangle. It doesn't really have to be a rectangle. That's just one that's commonly used because a lot of shapes that we use them for are rectangles. But you're using some sort of a shape and you're shading a portion of it. So we'll do an example of 3 over 4. Thank you. And so you draw a rectangle or a circle or whatever, and you split it into 4 equal regions, and then you would be shading 3 of them. Okay, so that would be a fraction 3/4 in an area model. We haven't seen a number line model yet. I didn't have an example of that one, but we'll do one now. So a number line model, we're using that same example 3/4. And we're going to mark off 0 at the beginning and 1 further over. So this is the value between 0 and 1. And then we partition into 2 pieces. So we cut in half and then in halves again. This piece right here, counting over, would be the number 3/4. And to mark it on the diagram, we would put a dot at that 3/4 mark. That's a number line model. And the last one is the set model. And the set model is the chips thing that we saw last time, where we're going to go with 4 chips. And then 3 of them are like shaded in. The chips model is fine when we have 4 chips and we're shading 3 of them in and we want to use the number 3/4. But if we had 5 chips and I wanted to know what is 3/4 of the 5 chips, that's not so easy. So it has some limited capacity use because of the types of objects we're working with. Whereas the first one, that area model, doesn't have that. With the area model, we can always divide it into whatever regions that we need to and so forth conveniently. In many of your math courses along the way, you're going to see the phrase fundamental law of, or fundamental theorem of, or fundamental principle of. Anytime they use the word fundamental, it's really important. So this is the fundamental law of fractions. This says let a over b be any fraction and n is a non-zero integer. Then a over b is equal to a n over b n. And we use this all the time. We use it both starting with the a over the b and making the numerator and the denominator sort of bigger, right? And we also use it from the a n over bn, and we use it to eliminate the n and make it a fraction that has smaller values on the top and the bottom. So we use this equality in both directions. We use it to make maybe the denominator a larger number when we're trying to get common denominators for things, which we will do. We use it to make things smaller when we're trying to put things in simplest form. So those are some things that you might be familiar with. So simplest form puts us at our next description. Simplest form is a rational number a over b, as long as b is greater than 0, where it has the greatest common divisor between the numerator and the denominator is 1. Or another way of saying that is that A and B have no common factors greater than 1. There's nothing in common that they can both be reduced by anymore. So that's simplest form. All right, I think we have an example next. All right, so here is a fraction. It's 7 over negative 14. Did I move too quickly? Do I need to back up? We're good? Okay. 7 over negative 14. And the directions simply say to write 3 fractions equal to this. So let me just say right now, there are infinitely many fractions equal to this. So your answers and my answers could be completely different and they could all be correct. So there's lots of things that we could do. Let me mention one thing that you might not think to do as an equivalent fraction just because it's possible, but we don't usually think of it. So right now you've got a positive 7 on top and you've got a negative 14 on bottom, right? An equal fraction to this would also be a negative 7 on top and a positive 14 on bottom. So that's the equivalent of multiplying the denominator and the numerator both by negative 1. So this would be one of the fractions that would be equal to this. So I'm going to open the floor to you guys. Somebody tell me another fraction that would be equal to negative 7 or 7 over negative 14. It is negative 1/2. That's its simplest form. What's another fraction equal to it?
14 over 28.
Yeah. So, remind me your name? Abigail. So when Abigail did hers, she actually reduced the 7 and the 14 by dividing them both by a common quantity. And is it Nathan? No.
Close. This was
You're Nathan and
Braden.
And when Braden did his, he multiplied the top and the bottom by something in common, right? So as we're looking for fractions that are equivalent to other fractions, we're allowed to do both things. And the reason that we're allowed to do that is because multiplication and division are actually the same operation. They're just inverses of one another. And so as long as we're doing one or the other, we're really doing the same thing. And you can think of it like this. When we multiply by 1/2, it's actually the same thing as dividing by 2. And so the multiplication and the division have these sort of inverse relationships. The other interesting thing that happens is that because we now got from Abby that this is negative 1/2, we could actually start from the negative 1/2 and create fractions maybe even more easily that are equal to this than we could from the 7 over negative 14, right? For example, I could create the fraction of 2 over negative 2 over 4. Well, negative 2 over 4 is very easy to see where it came from when I'm looking at the 1/2 part. Not as easy to see if I'm looking at 7 over 14. But it's still equal, right? Because they're all equal to one another. So if you're asked a question to find equal fractions, make sure your signs are correct, of course. But aside from that, you've got lots of options, whether you're multiplying or you're dividing, to find equal fractions. We're going to look at simplest form, and I always use this as an example because what I want you to see that you cannot do, but it's really tempting, is to cancel what? What can you not cancel? You cannot cancel the exponents. Okay, so simplest form has to do with multiplying and dividing, not, in this case, it would be like square rooting, right? I'm not allowed to just take the square root of the top and the square root of the bottom, and it will become equal to the same thing it was before. It's actually not a true statement at all. So there's no canceling the squareds. So what that means is that we must, use them. So in other words, I've got 42 times 42, and I've got 35 times 35. And if I had it cubed or to the power 4, I'd just repeat them that many times as well. So I can multiply the 42 times 42 and the 35 times 35, but I don't think that's very productive. The goal is to reduce it, right? So making it bigger would be sort of counterproductive to doing that. But what I can do is I can look at the individual values. Since everything is multiplied on top and everything is multiplied on bottom, I can consider them sort of individually. In other words, the 42 and the 35, like one pair of them. What do they have in common? Not 5, 7. Yeah, they have a 7. I'm going to get a 5 by doing that. So if I divide these both by 7, I will get 6 and I will get 5, right? Just a little darker. But I can do that again, yes? I can also divide this 42 and this 35, again, by the same 7, and I will get a 6 and a 5. Now notice on top, all I've got are 6s, which they break down into 2s and 3s, I get that, and all I got on the bottom is 5s. So there's nothing that the 6 and the 5 have in common, right? Which means there's no more reducing that I can do. So now it's time to go ahead and do the multiplying that we could have done at the beginning. So on the top, I have 36, and on the bottom, I have 25. And I don't even really need to check to make sure that the 36 and the 25 don't have anything in common, because the 6 and the 5 didn't. But if you want to, you certainly can. But at that point, you're finished. Any questions? Okay. So we're going to continue on with some different theorems along the way. Theorem 6.2 is one that you know and love, and you've used it all the time, and you knowingly refer to it as cross multiplication, right? Cross multiplication, right? So it says that equality of fractions, two fractions a over b and c over d are equal if and only if AD is equal to BC. And for a visual for this, you probably remember something like this. That's an A. It looks kind of like a Q, but it's not. AB over CD, and somebody saying, hey, these are equal, and if so, then you can cross multiply. Maybe they did it like this with X's. Maybe they drew circles so they made it look like butterflies. Right? Do you see my butterfly now? There's a butterfly there if you wish. So visual imagery is really helpful for a lot of people with mathematics. So what this is saying is that if I can multiply those diagonals and end up with the same quantity along each diagonal multiplied, then my original fractions were the same to begin with. So what we're going to do in the next problem is we're actually going to decide if two fractions are equal. But we're going to do it in a variety of ways. We'll start with the one that I just mentioned because it's certainly a viable option and we should use it because we just had a theorem on it. But there are other ways to determine excuse me, if fractions are equal. So I'm going to show you three other ways, and I'm not even promoting that this is like all the ways possible, but I want you to see several options. So one of the things that you're going to experience through this course and any other of the elementary math courses that you take here at OBU is that we like to show you lots of ways to do things. Those of you who've had these courses before know that. And the reason we do that is because not all of you and not all of your students learn the same way. And so while this method, the one I just showed you, may make perfect sense to you, some kid somewhere is not going to know what you're talking about, or they're just not going to like it. And so you're going to be like, okay, well, we're not going to cram it down their throat. If I have another option that they like better and it still works, then we should have another option. And so showing lots of options is really a big component of our textbook and of current teaching trends actually as well. So the first way that we will do this is we will do this with, they call it Theorem 6.2. Yeah. So we'll do Theorem 6.2 style. So Theorem 6.2 says, I can write down the three. Let me just make one comment first. They're both negative. Agreed? So can we say that that's cool and ignore the negatives? Okay, we're going to do that. So we're not going to include the negatives. I know they're both negative. I really just need to know if a 3 over 12 is equal. This is sort of like a question mark for us to the 36 over 144. One of the things that you will also notice that I do as I'm showing you different methods is that I will also point out sometimes maybe drawbacks that you didn't consider to particular methods, why it might not always be the best choice, even if it's your go-to choice, or why somebody might not be liking to use it, or maybe what makes it preferable to be used. So sometimes efficiency, in historically speaking in the past, efficiency is the driving force of mathematics. Efficiency does not always promote understanding, and vice versa. And so this one right here does not have a whole lot of understanding behind it. You know you can do it. I just told you you can do it, but I didn't prove to you that it's possible or why, did I? I didn't. And we don't have enough tools at our disposal for me to actually justify it fully right now anyway. But it does work. So one of the drawbacks, however, is that in my multiplying, I have to be able to multiply 3 times 144, which you're probably not going to do in your head. Right? Like realistically, you guys are probably going to grab a calculator. If you were doing this with your, 5th or 6th or 7th graders or whatever, you're probably going to have them using, scratch paper to do this or whatever. And 3 times 144 is not super helpful. And 12 times 36 is not any better. They both have their reasons for why they're not super helpful or super easy to do, but that's bigger multiplication than just single-digit multiplication, which might make this a less than desirable approach. So, if you do have a calculator, what is 3 times 144?
432.
432. And what is 12 times 36?
432.
Yes, it is. So they are in fact equal. And since the cross multiplications are equal, the original fractions were as well. So yes, they are in fact equal. So this is one way to do this. Let's see which one I want to do next. Let's do simplify next. So this is method 1. If the fractions themselves are not in simplified form, another option is to simplify and compare. Basically, if I can simplify them both down into such a form that they're equal to one another, then they're equal in their original form, okay? If when I get them completely simplified into their simplest form, they're not equal to each other, then their original forms were not equal to each other. So we'll do them one at a time. I have 3 over 12. So we can multiply and we can divide, and here we're looking to simplify, so we're going to divide. What do 3 and 12 both divide by? 3. So we're going to divide top and bottom by 3. 3 divided by 3 is 1, and 12 divided by 3 is 4. Excellent. On the next one, we have 36 over 144. So you may recognize immediately that 144 is divisible by 36. I wouldn't, I look at numbers pretty constantly, and I still wouldn't think that when I looked at this number. But I would probably look at this and at least know that there's a 12 in them. At the very least, you should look at this and say, hey, they're both even, so I can divide them both by 2. So we're going to divide by something, even if it's not the biggest something that there is. That we see. And so I'm going to go with 12. Most of your kids will have learned their multiplication facts, if they remember them, through 12s. Seems to be the going number of these days is through their 12s. So 12 is a reasonable thing for them to potentially know. These numbers are both divisible by 12. So 36 divided by 12 is 3. And then 144 divided by 12 is 12. And then 3 and 12 will both divide by 3, which we just did a minute ago. So we know, in fact, that those are going to give us 1/4. So these two are equal, and it checks. So the original ones were equal as well. So you can imagine simplify and compare is really nice when things actually are large enough that simplification sort of makes sense. Or maybe they aren't so large that simplification is simply difficult to do. Ugly numbers, things like that. Let's do the next one. We'll do common denominator next, specifically common denominator. The last one we're going to do is going to be least common denominator. So general common denominators are found by simply multiplying the two denominators by one another. Okay? So right now we have the fractions 3 over 12 and 36 over 144. So again, common denominators, just generally speaking, and sometimes it becomes the least common denominator too, but generally speaking, common denominators just mean we multiply the two denominators by each other. And of course, anything you do to the denominator of a fraction, you have to do to the top. So the first fraction gets multiplied by 144 over 144, and the second fraction by 12 over 12. We happen to have already multiplied 3 times 144, so we know it's 432. So we'll kind of go off of the fact that we've done that already today. We haven't done the 12 times 144 though. So what is 12 times 144?
1,728.
Awesome. Now that denominator is definitely going to match down here because I still have 12 times 44. And we did the 36 times 12 earlier as well, and we got 432. So using common denominators, the denominators guaranteed are going to match when we do this. We're looking then at comparing or contrasting the numerators, and they're equal. So these two things are equal. So again, it checks out. But common denominators are sometimes overkill, especially we're here. I don't need common denominators. A least common denominator would be so much preferable because it would keep the fractions values, individual values, pieces smaller. So if I'm going to do step 4 or option number 4, a least common denominator approach, what I'm looking for is I'm looking for something that I can multiply one of the fractions denominators by and get the other one. And if that's not possible, looking at something I can multiply each by to get something smaller. Smaller than the whole thing, basically. So in particular, because of these numbers that we're given, 12 and 144 are actually very convenient numbers. I mean, again, we know our multiplication tables up through 12s. That's the standard these days. And so multiplying the 12 by 12 will give me the 144 to have a common denominator, and a much smaller common denominator than the 1728 we had before, right? So again, if we multiply the denominator, we have to multiply the numerator. And that gives me the same 36 over 144 that I had before. So they check out to being equal. Any questions on those? All right, so Theorem 6.2 talked about cross multiplication, proving that things are equal. The next theorem is very similar, but instead of proving that things are equal, it actually talks about when a value is larger than another value. So like greater than or less than kind of things. So it says if we have a, b, c, d in integers and the b and the d, the denominators are not 0, then a over b is greater than c over d if ad is greater than bc. So we're still cross-multiplying, and we're keeping the direction of our inequality the same. So this is the first sort of diagonal, top to bottom. So we have to multiply a times d. And this is the second diagonal, and we multiply b times c, or either way. And then the inequality direction stays the same. So if, in fact, when I do the cross multiplication, I get a greater than symbol, then the original one is greater than symbol. If I got a less than symbol, it would be a less than symbol. Okay? This is a very convenient tool when you're comparing two fractions only. It doesn't have sort of an analogous, well, what if there's three fractions? Can I see if the three fractions, compare and put them in order? So it doesn't become super useful in this particular problem. Because this problem has three different values that I'm comparing. Now, you could take them two at a time, but that would be very tedious. You take two of them and decide which one's in order, and then you take another one with one of them. I mean, you might have to do this process 3 or 4 times before you get the exact ordering that you're looking for. You could do it, but it might be tedious. So that's probably not the approach that we would want to go with. However, we could do some of the other things that we were doing over here. We're either reducing to get things in their smallest form and comparing them. Sometimes that's helpful. For example, if I was comparing numbers that were like 1 over 4 and 1 over 5, those are the reduced, simplified versions of something, it'd be clean and nice and neat because they have the ones in common on top, right? Or if I'm comparing something that's reduced where the denominators are the same thing. Yes, ma'am?
Could you also just like divide the top by the bottom and then compare the decimals?
That's a very good question, and I'm really glad you asked it. So in a real answer to you, the answer is yes. If you're confirming your work, you can definitely do that. But here's the problem. We're working with fractions, and we haven't worked with decimals yet. So decimals are in Chapter 7, and there's actually a reason for that. And oddly enough, as much as you might feel like, well, I really like decimals so much better than fractions, fractions are taught first in school. And so everything that we do in decimals is actually based on what we've done before in fractions. So for now, for the purposes of proving whatever you're trying to show or whatever, no, you can't. But if you want to check it with your calculator on your own or whatever, you definitely can. So yeah. Okay, so, I meant to mention this one over here. The common denominator, least common denominator, however, is a really good one for comparing things. So getting things that are either on the common on the numerator or on the denominator is helpful, and the denominator is simply more common to do. We see it used more frequently. So as we're taking a look at these, we would like to get those three denominators to be all the same. Whoops, highlighter's what I meant to do. And that's actually not too bad of a thing to ask for these particular fractions. What fractional denominator would be nice for these three? 20. And one of them is already in that form, right? So one of them is good to go, the 13 over 20. So I'm just going to rewrite it over here. The next one is 3 over 5. So what would I need to do to get the 3 over 5 to have 20 as its denominator?
Multiply it by 4.
Right, multiply it by 4, and I would get 12 over 20. The last one is 7 over 10. And what would I need to multiply it by?
2.
Yes, and 2 over 2 is what you mean to say, right? 2 over 2. So we would end up getting 14 over 20. So these are now the three that I'm actually comparing. And it says ascending. What's the word ascending mean? Getting bigger, right? Like we ascend a staircase. So sometimes they ask questions and they say ascending, sometimes they say descending. Just pay attention to directions. Ascending, we want the smallest one first. So which one's the smallest?
12.
Yeah, the 12 over 20 is the smallest. And I want the actual original fractional value that 12 over 20 represented. So that would be 3/5. You can either put a comma and continue on, or you can put a less than symbol. It doesn't matter to me. If you're going from the smallest to the largest, a less than symbol would come next. What is the next largest if I'm ascending?
13.
Yeah, 13 over 20. And that's actually the form it was given to me in. So 13 over 20. And then, of course, my last one would be the 14 over 20, which is the 7/10. You bet. So this would be my ascending order in my fractions. So I mentioned that the theorem I just showed you is not super helpful to this particular problem because there were 3 things I was comparing. However, in the next problem, I'm actually comparing just 2 fractions. So it is an option that you can use. So we'll use that option first simply because we haven't had an opportunity to do so. But then I'll show you a couple other ways to answer this question that are perfectly reasonable given the particular fractional values that they're showing you. So we can actually cross multiply these. Okay, I'm not putting an equal sign between them because I'm going to guess that it's probably not equal. It uses another symbol between them, and I don't want to put an equals and then have to change it because that's sort of strange. But we can simply multiply 21 times 215 and 51 times 430. So what is 21 times 215?
4,515.
Okay, and what is 51 times 430?
2,100.
930? 930 is what I've written down. Is that right? Yes? Is that okay? Did I write them right?
Yeah.
Okay, good. So obviously, which one's bigger? 21,000, right? So if I sort of follow that back up, I've actually shown that the first one is smaller than the second. That's the symbol that would go between them. So this is sort of option 1. I think it was called theorem 6.3. So option number 2 is going to be that common denominator approach that we've done before. Again, because these particular denominators lend themselves nicely to that. Take a look at 430 and 215. What do you notice?
Times by 2.
What's that?
Times by 2.
Yeah, 430 is just a multiple of the 215. So if I were to take the first one, which is 21 over 430, and then the second one, which is 51 over 215, and I were to multiply this denominator by 2, I get the same 430. And what's my numerator now? $51 times 2 is 102, right? Whew, goodness, it's a hard day, isn't it? 102. Okay, obviously, 102 is bigger than 21, yeah? Okay, so the first fraction would then again be smaller than the second fraction, proven by using common denominators. Okay, so common denominators would be another option. Either common denominators or least common denominators. I'm kind of using them interchangeably here. You certainly could get a simply common denominator if you wish. But there's actually another approach that's really good, and you might not have necessarily thought to do so, but if you were really looking at this from a real world perspective, it's probably what you would use, and that's estimation. So if you're looking at these, and you notice, as Braden did, that the denominators are kind of like one's double the other one, you should be able to look at the numerators and be like, hey, but that second, right? Like this fraction, let me clean this up. Fraction number 1 has a smaller numerator with a bigger denominator, right? You're taking fewer items and you're spreading it among or dividing it up into more pieces. The second one is a bigger numerator and you're dividing it up into smaller pieces, right? So imagine you had 21 cupcakes, and you divide them up into 430 people. Well, that's not good. And while 51 cupcakes divided by 15 is not much better, they do almost get a quarter of a cupcake, right? They do. It's very close. So you can think of this in terms of like mental math or estimation. if that's how you choose to justify something, it just means you have to write it out in words. So the first fraction has a smaller numerator and larger denominator, making it smaller automatically, smaller than the second. Okay, so it requires some justification. You could use an example if you wanted your justification too. Maybe instead you had 21 pizzas and you're dividing it among 430 people. That might make more sense than cupcakes or whatever. Okay, any questions on those ideas? So in your book, generally speaking, it doesn't tell you have to use this method. There are going to be some sections where we're going to have a little bit more structure, and it might tell us some things like that. So you get to pick. Doesn't matter to me. But just so that you know that there are multiple options, and depending on the numbers you're given, you might not even use the same option all the time. All right, I think this is the last theorem for today anyway, theorem 6.4. Is that true?
6.5.
No, I've got, Oh, no, I've got 6.5 underneath it. No, they're on the same, yes, they're right together. Theorem 6.4. Theorem 6.4 is the denseness property for rational numbers. It says, given any two rational numbers, different rational numbers, a over b and c over d, there's another rational number between these two numbers. So intuitively, that should make sense to you, perhaps from a number line perspective. If the two numbers are not the same, they have their own individual location on the number line, well, there must be some space between them. And you can always find half the distance between any two numbers, right? And you can find subdivisions beyond just half. But there's space, right? There's this idea of space between values. And that's all that this is talking about, is that there's infinitely many numbers between those two numbers. And this next one is one that you may not be aware of, and it's very clever. It's far easier than what I just said, which is taking two numbers and then, like finding the middle point. Sometimes that's really nice, right? Like the halfway point between, say, like 2 and 4 is 3. Super easy, no problem, right? But sometimes with ugly fractions, this is not super easy, because to find the halfway point might mean to find common denominators and then divide by 2, and it's kind of messy. So this actually tells us a very nice way of finding a rational number in between two rational numbers. So if a over b is less than c over d, then you can actually add the two numerators together, and you can add the two denominators together, and you can set up another fraction, and it will be between the two fractions that you had to start with. That's easy, because the numerator and the denominator are usually just whole numbers. So adding the two numerators together, adding the two denominators together is usually quite a simple process. So for example, this is super ugly. I don't know about you, but I do not want to find the common denominator of 427 and 92. I don't. And that's what we'd have to do if we sort of thought about it from a subdivide halfway standpoint, like I mentioned first. Thankfully, we have another option. We have theorem 6.5, which says what I can do is I can add the numerators together. Well, that's 33 plus 7. And I can add the denominators together. So that's 427 plus 92. And I've got, let's see, that's 40 on top. What do I have on bottom? 519 is what I have written down. That's probably right. 519. And if you wanted to confirm in the sense of concretely on paper, you could do any of the methods we did before where we were comparing things, right? Cross multiplication, common denominator, all that kind of stuff. Or you could do, as Abby suggested before, of well, could I try this? At least from an intuitive perspective, you could verify to yourself that this really worked by taking your calculator and saying 40 divided by 519. And it's this decimal, and you write out 3 or 4 decimal places, and you do the same thing with the first two fractions that they gave you. And you could verify from an approximation standpoint with your calculator that it does in fact give you a value in between. So this is a very clever sort of approach. There is this question that says, why must there be a number between these two fractions? So why? Why must there be?
There's infinite numbers and those aren't the same numbers, so there has to be something between them.
Okay, so I want to take what you said and make one change and use the word space or distance, okay? So we'll use space. There's space between the two numbers because they're not equal, right? Therefore, there are, we'll say numerical values representing those points. And it's probably a wise idea to recognize that this is exactly what this denseness property said, right? And it's the same justification for it. This is actually coming from the denseness property, which is theorem 6.4 if you wish to write that. The denseness property. Okay. Let's take a look at example 8. A student simplified the fraction m plus n over p plus n to m over p. First question, what did the student do?
Crossed out the ends.
Yes. So they crossed out, and in fact, they might have even in their mind thought of the word cancel, right? People like that word. It's a little scary of a word because it means lots of things sometimes. So canceled out the ends. Not just the n, but the plus n, right? They canceled out the plus n's. Why might they believe that this is a valid operation?
Because they see that it's on the top and the bottom, and using past math experiences, we know if like 5 times 2 over 6 times 2, you can cancel out the 2's.
So,
The opposite of subtraction.
yeah, so they might think about adding an opposite subtraction, but they're still also probably doing something with multiplication, I think, which you hit on at the very end. So they are utilizing, or they're trying to, the idea of reducing fractions to simplest form. With division, right? So if it were an over pn, what are those my letters? Oh, it's mn over pn. If it looked like this, it didn't have the plus between it, right? It was actually multiplication that was happening. We've marked them out, but what we're really doing is we're really dividing them both by n, right? That's what happens when we mark out a multiplication with simplest form, is we're using division. So they're using a property that's appropriate for division, but they're using it with subtraction, like you said, right? Like they're trying to subtract off, or they're trying to cancel out. So there's something that they've seen along the way that's sort of right, but they're using it in the wrong context, okay? So we could explain that to them, and that's fine, and that's probably worth explaining to them in general. Hey, you can do this with multiplication and division. You can't do it with addition and subtraction. What if they say, but why? Any thoughts as to how you might be able to show or prove to the student simply that this doesn't work?
Maybe by working it out with a smaller number.
With numbers, yeah. Numbers are wonderful. If you can show something in a numerical form fails, then it has to fail sort of in general because it didn't work all the time, right? So find some numbers, pick your favorites, it doesn't really matter. So we'll do 3 plus 2 and 5 plus 2. So if we could do what the student wanted to do, we would cancel out the plus 2s and we would get 3/5. Agreed? That's what the student says. If we don't do the cancellation, and we actually just do the addition from the top and do the addition from the bottom, what do we get? 5/7. And what kind of argument can you make for me that tells me that these are not equal? Why is 5/7 not equal to 3/5?
Because 7 and 5 do not have anything in common.
That's not exactly why, but you're on the right track toward getting there. Abby?
When you like cross multiply 25 and 21 don't equal.
Okay,
There's something
So that's
about
one of
5 and
them.
7 can't break down anymore.
there's that too. So you guys, if we'll combine all these pieces together, we'll have several options to think about. Okay, so back over here, one of the things that we did is that we showed fractions were equal, right? Here and here, we put things in order, right? Not here, that's not the one I want. Here. We talked about whether things were equal, and there's lots of ways to do that. So one way to do that is to do cross multiplication. So you looked at those two things, you tried to cross multiply, and you're like, they don't work. If you try to cross multiply, they don't give you the same value. That might be justification enough for the student. Another justification enough for the student might be to recognize that the numbers that we actually had there are both in simplest form. 5/7 and 3/5 cannot be reduced anymore, and they're not the same. So they're clearly not equal because they're in reduced form, they are not the same. You could get a common denominator and justify from there. Another option that we haven't really talked a whole lot about because we did it last class period is you could actually draw a picture. Could you draw a picture of 5/7 and a picture of 3/5?
Yes.
You probably could. In order to compare fractions, it's often easier to do things in like fraction bars so that they're the same length. So if you have one length and you make it 5/7 that you shade in, and another one that you make 3/5 and you shade in, you can compare the shadings a little bit easier. Sometimes people want to do like pie charts. That doesn't always help because remember we saw that one where that was shaded in, it was like 2/7 shaded in, and at first glance the picture looks an awful like 2/8. And so visually it's not as discernible with a circle diagram. But rectangles that are the same length really work very nicely. So any of those would be good ways then from this point to be able to show the student that they're not the same. So I'm just going to list a few of them. We could do the cross multiply. We could talk about the fact that they're in simplest form and not equal. We could get a common denominator or a least common denominator. We could draw a picture. What we can't do is probably just stop where we are and say, see, therefore it doesn't work. They're going to be like, okay, well, I didn't understand before and I still don't understand, right? Probably needs a little bit more than the fact that, oh, look, I did this and I got 5/7 one way and I got 3/5 the other way, right? So now what? Probably needs a little bit more than that, but that's something that we could take a look at. So here's what we're going to do. We have one last question to do. We're going to do it next class period. So we'll do this one last question. We will go into section 6.2 next time, but we will stop early enough in the class period that you'll have time to do the group work for 6.1 at the end of class. Here's what that means. It means that you will probably have homework both on Monday and Wednesday next week, just so that you're aware. That's probably going to end up getting doubled up, okay? So have a great weekend, guys.